module B of the electrical technology curriculum, which is typically on the ACs, the alternating current, which is actually a vital mode of electrical energy, the alternating current. Okay, so the problems that we have solved so far, the battery that we use is basically DC, but AC is the prevalent mode of electrical energy transmission and usage. Okay, as I told in the previous class, maybe 100 years ago, there was DC, and to a considerable extent, and people used the generation was DC, and usage was also DC, and but gradually AC was discovered, and the efficient ways of transmission of AC and usage was found, and so people went to DC, but still there are DC applications in some very primitive locations, in primitive houses. Okay, some old palaces, and also, as I gave the example of some places in Kolkata, there is still DC, and there are some very prominent, DC applications. I mean, apart from whatever we are using today, like computers and all, but there are a lot of DC applications also, and because DC has its own inherent advantages also, but there are disadvantages also. So all these things come into the picture. So one prominent example I gave in the previous class was that of the Calcutta tram, which is basically DC. It's still DC. Now, so from module B, we will start what is called AC. That is, here the voltage sources is basically a time varying quantity, and it is also not just simple time varying function, but it is having basically a sinusoidal nature, where Vt is equal to Vm sine omega t, or it could even be cos omega t also. Now, this Vm is basically known as the amplitude of the voltage, and or magnitude, and you all know how Vm sine omega t will look like. So this omega is basically the angular frequency, which is radians per second, which is defined as 2 pi f, omega equal to 2 pi f, and f is in hertz, and f is again equal to 1 by t, the time period of the waveform. F equal to 1 by t, time period of the waveform, we all know. So this f is again the frequency, is basically the supply frequency, the frequency that we enjoy, the power that we are, most of the places you enjoy in your household, in your hostels, that will be there is uh, of a particular f. Okay, and this f actually varies from country to country, and typically there are some values, like most of the countries of the world, the frequency is basically 50 hertz, which is in India, but USA and Canada, some of the frequency is basically 60 hertz. And as I gave some example, there are some applications where the frequency is even higher in aircrafts, rockets, or some military applications. The frequency is higher, which actually comes from the design aspect, and so that is just for your knowledge. Those of you who will be studying actually electrical engineering, so there are definite reasons. There are definite technical reasons for this choice. Okay, the choice to attain certain efficient conditions, but again it leads to some other disadvantages also. So these advantages and disadvantages that have to weigh, and these choices are made. These other frequencies like 400 hertz. Okay, please mute your background if somebody is having the background. Okay, so this is the symbol of the alternating current, alternating source. It could be a current source, it could be a voltage source, and the equation that we have just written, Vn sine omega t, basically looks like this. You can draw a better graph also by by using some software. I just did by hand. It looks like this, but the sine wave, it is it is a periodic, and so we are plotting with respect to omega t. Okay, so at 2 pi it becomes the one full cycle. So from 0 to pi is one half cycle, and the peak is achieved at pi by 2, and the minimum is achieved at 3 pi by 2, and so on. So the maximum value is Vm, the minimum is minus Vm, and it alternates between these two. Now, as I told, this it is just a sinusoidal nature, so there can be hundreds of such sinusoidal, curves. So suppose we have this V1 equal to Vm sin omega t and V2 equal to Vm sin omega t plus theta. That means both are having the same magnitude, but the first one is having omega t, the second one is having omega t plus theta. And we all discussed how it looks like. So both of them are basically between plus Vm and minus Vm. But the first one is omega t at omega t equal to 0, its value is 0. The second one is 0 basically at omega t equal to minus theta. Okay, at some minus theta angle, omega t equal to 0. So V2 is basically a shifted version of V1. Okay, it is basically a shifted version of V1. It is it looks like this. So we basically write it as V2 sin omega t plus theta. So this is how we make the difference if they are shifted from each other. Okay. Now, suppose you have V1 equal to Vm sin omega t, V2 equal to Vm sin omega t plus theta. Now they look like this. So we call it that what? V1 lags V2. Okay, V1 is lagging V2. What is the meaning of lagging, leading? Okay, if somebody is lagging, then we can call the other way as V2 is leading V1. Okay, so they both way you can tell. If somebody is lagging means you can tell the other way the other one is leading. So we will understand this. What is the meaning of this lagging and leading in this type of alternating quantities? And here we have typically drawn the voltage in terms of voltage, but it could be even a current having this type of sinusoidal nature. So we did this example that suppose you have this V1 equal to Vm cos 5t plus 10 degree and V2 equal to Vm sin 5t plus minus 30 degree. Okay, so both are having same magnitude, but one is represented in terms of cos, the other is represented in terms of sine. And for both the omega is fixed. Okay. Now since the omega is fixed, so this can be basically represented in the term of phasors. We gave this phasor notation in the last class. And so obviously in phasor, there has to be a reference and there has to be a fixed direction in which these phasors are moving. Okay, and we assume that the counterclockwise direction is the positive direction. And suppose your eye is placed here, okay, then how do you look like? So V2 equal to Vm sin 5t minus 30 degree. That means it is lagging. Suppose we consider as the sine only, so it is basically lagging the reference by minus 30 degree. So what we do is we take this magnitude of Vm. So the length of this phasor is basically the proportional to the magnitude. Okay, some scale is chosen, and so the length of the phasor is basically proportional to this magnitude Vm. So that is how V2 is drawn. Now to draw V1, basically you have to convert it with the same trigonometric quantity. Since we have chosen sine, so this has to be converted to sine. Okay, you all know how to go do this. You all have been doing this trigonometry. You must have solved several thousand questions on trigonometry. Okay, so Vm cos omega 5t plus 10 degree is equivalent to Vm sin 5t plus 90 degree. Okay, so now you plot this. So where will this phasor be? It is having an angle of plus 100 degree. Okay, so the angle will be somewhere here, plus 100 degree. It is more than, obviously with respect to the reference. So everything is being drawn with respect to the reference. But it is also having a magnitude Vm. So magnitude wise, it is the same. Okay, so at plus 100 degree, we will having a phasor. This is the V1, but its magnitude is the same as V2. Okay, so V1 and V2 are having the same magnitude, but the phasors are located at different angles with respect to the reference. Now, so here this is, if you see this V1 is leading, since the phasors are rotating in this direction. Okay, V1 is ahead of V2. V1 is ahead of V2. That means V1 has already crossed V2 and arrived here. So we can read as V1 leads V2 by 130 degree. That means you calculate the total angle, and that is how we represent V1 leads V2 by 130 degree, or you can conversely, you can even write V2 lags V1 by 130 degree. So both of them are correct. Now, so this also we did that. So once we apply this type of voltage into a circuit, okay, obviously there is a source. So the symbol of this alternating source is given by this round with respect and this type of sinusoidal symbol inside. So that is how it is represented. And we saw that the value of current, we did the detailed derivation in the previous class. Okay, so we will not do the derivation. So the current that is generated will be of this form. So its magnitude is Vm by root over r square plus omega square L square. So magnitude is okay. So this denominator basically will have the dimension like resistance. Okay, the denominator is almost having a dimension like resistance. If you put omega equal to 0, omega equal to 0 means what? It is what is the meaning of omega equal to 0?
DC current.
Huh?
So DC current. DC.
DC. It is
DC
basically
source.
DC. Okay, so omega equal to 0, then you see that in the denominator basically it becomes R. Okay, the denominator is R, that is basically the uh, voltage by the resistance. Now this cos omega t minus theta, since the voltage is cos omega t, so due to this RL, L effect, there is a generation of the current is at an angle minus theta from the voltage. So how does it look like? Now this theta, how do we find the theta? It is found out by tan inverse of omega L by R. Okay, so this is how we find out theta, and this is the value of this is how it is represented. It equal to Im cos omega t minus theta. Okay, it is equal where Im is given by Vm root over of r square plus omega square L square, and cos omega t minus theta. So if you draw the phasor, we have done this in the previous class. If you draw the phasor, you see, okay, so this is the reference, and the phase associated with the voltage is basically what? Omega t plus what? 0. Okay, so if we align the voltage phasor along the reference, if we align the voltage phasor along the reference, where will the current phasor be?
So theta degree behind the reference, like
Theta degree
in the
behind.
clockwise direction. In the clockwise direction.
So see, it is lying 30 degree behind. Sorry, not 30 degree, but theta angle behind the voltage phasor. And since we are doing the anti-clockwise rotation, if there is the I, it will first see the voltage phasor. Then after angle theta, it will see the current phasor. And this theta is basically given by tan inverse of omega L by R. So if you are given an RL circuit, okay, if you are given an RL circuit and the supply frequency is known, that is F, so F is equal to omega is equal to 2 pi F, then you can find out what will be the value of theta, how much the current will be lagging behind the voltage by this formula. So the magnitude of the current you can find out Vm by root over R square plus omega square L square. And this theta is given by this tan inverse of omega L by R. So all of you have calculators and you can do this. Now there are some, so IT basically lags Vt by theta. Okay, since this is an RL circuit, yes.
So we will put always V of t on the reference, or we can put I of t current on reference.
No, see, you can put it anywhere, but the relative angle between them will be the same. Okay, but it depends upon the way I have given. I have given Vt equal to cos omega t plus 0 degree. Okay, so the phasor is, the phase angle is basically 0. So it is kept with respect to the reference. Vm cos omega t. Okay, so it is, since the plus part is 0, so it is kept along with. If it was some other angle, we will see. We will do numericals also. I will ask you to do numericals where this may not be there. So you have to generate the angles correctly accordingly. Okay, but the difference between V and I will be given by this theta, tan inverse of omega L by R. Okay, so you have to, if you are given some other V, suppose if you are given some other V, then you have to generate the theta and put the current phasor accordingly. Okay. So we did this. If omega equal to 0, it is basically DC. Omega equal to 0 DC, and so far we have done a lot of numericals on DC, but gradually we'll be entering AC. We have just entered AC, and we'll see that as soon as this AL and C are put into the circuit, how it behaves. So if you put L equal to 0, it's basically pure resistance. Or if omega equal to 0, it is pure resistance. There is totally the resistive effect. So if you L equal to 0, basically this. So even if you have L equal to 0, but we apply an alternating voltage. So what basically will happen is, because of L equal to 0, if you just put in this equation, what will be theta? Tan inverse of 0?
Zero.
Zero. So theta will be 0. So what will happen? It
There
will
will be no
eventually
lag.
lead to
Will be in phase.
VT and
Both will be
IT
in phase and there will be
Will
without
be in
any
phase
lag.
with each other.
So VT and IT will align. Okay, as I use the word align, so they are basically aligned. So if you draw the phasor diagram, they are basically lying exactly together, the VT and IT. But you see the arrows are different because they have different magnitudes. Okay, because IT is generated, that IM is generated by VM by something in the denominator. Okay, so its magnitude will be different. It will not be the same as the VT. Unless it is some other special case like 1 ohm or something like that. Okay, but otherwise, its magnitude will be different. It can even be greater also. Okay, depending upon, suppose the value of R is less than 1, then the value of IT may be greater also. But it is not exactly equal to VT unless again R is equal to 1. Otherwise, it will be the value of IT, the magnitude of the IT will be different from VT unless there is a special case. Now, if your R is equal to 0, okay, so if you R equal to 0, if you put it here in this formula, what will be the angle theta?
90, sir.
Omega
Pi
L by
by
0, omega L by R, omega L by 0 is infinity. Tan inverse infinity is
90.
pi by 2. So your theta becomes equal to pi by 2. Okay, so if your theta becomes pi by 2, what will happen? How will the phasors look like? So your VT and IT will be
Perpendicular to each other.
so VT and IT will be perpendicular.
Lagging.
Yeah, so VT and IT will be perpendicular to each other. And if you align the voltage phasor along the reference, and the current will be lagging the voltage by 90 degree. Theta equal to, yeah, so if your voltage phasor is along the reference, okay, if your voltage phasor is your reference, the current phasor will be 90 degree away. Okay, it is perpendicular. So that will only happen if it is a pure inductor with zero resistance. Okay, it is a pure inductor with zero resistance. So whatever we are showing is basically, this is how it goes mathematically, but it may not happen because any inductor is basically a piece of coil, a piece of wire, which will invariably have some resistance also. But mathematically, this is a situation. If there is a hypothetical situation where there is a coil with zero resistance, then so it is basically a pure inductor. In that case, the current will lag the voltage by exactly 90 degree. Okay, so
Excuse
some of
me,
you,
sir.
yes.
Sir, what is the significance of lagging behind and lagging front? Does it means that voltage comes first, then current will be generated later?
Not voltage comes first, current will be. See, if you plot the waveform, we have shown that what is the meaning of lag lead in the when we plot the waveform. They are shifted away. They are,
Means voltage achieve peak value
yes,
before
the
the
peak values. Those things will happen. We showed in this this type of situation. Which one is lagging, one is leading, but so the peak value will appear at different times. Okay, so if you
Okay,
plot
sir.
it in that case, that current, it will have a different magnitude, and it will be shifted accordingly.
Okay, sir.
Okay, so that is so that is the lead lag. Gradually we will be having more of these, because as we just saw, if we put L into the circuit, we put C into the circuit, something else will happen. We'll see. Now before that, we will have to do some. There is something called the average value of a sinusoid. So we have chosen Vt is equal to Vm sine omega t. Okay, so it is varying with time. Okay, and we saw that it is sometimes having positive value, sometimes it is having negative value. Okay, so this sometimes it is having positive value, sometimes having negative value. So if it is found out, if it is asked what is the average value of the sinusoid. Okay, so the average value of the sinusoid is defined as, the area under the curve divided by the time. This area under the curve divided by this two time. So the average value or current of a periodic waveform, whether it is a sine wave, okay, it could have been a square wave also, or it could be a triangular wave, is the defined as the quotient of the area under the waveform with respect to time. That is the area under the waveform divided by the time. Okay, so in other words, the averaging of the instantaneous values along the time axis with time being one full period. Okay, for the full period you have to do the averaging. But what will happen in this case? Above the omega t axis, in the upper half of the omega t axis, the values are basically positive. And below the omega t axis, the values are basically negative. So, and assuming that they are, pure sinusoidal, okay, so the area will be what? For the first,
Zero, sir.
Zero.
Total area will be zero.
yeah, because
For the full period.
from 0 to pi, the value will be positive. From pi to 2 pi, the value will be negative. So if you add them, the value will be 0. So the average value will be 0. Okay. So with 0, with 0 value, you cannot work with 0 value. So because there is some finite value, though if you consider the whole half full time period, it becomes 0. So what is actually done is, so for a periodic waveform, the area above the horizontal axis is positive, while the area below the horizontal axis is negative. So this makes the average or mean value of the symmetrical quantity 0, because the above the horizontal axis it is positive and below the horizon is negative for the half cycle, and so they cancel each other. So the average or mean value of a symmetrical alternating quantity such as a sine wave, what is actually done is, instead of the full cycle, if you take the full cycle, the value will be 0. So it is measured with respect to one half of the cycle. Okay, so over one half of the cycle, okay, so it is done from 0 to t by 2, the half of the time period, or in this, if you consider with respect to the omega t, it is done, the averaging is done from 0 to pi. So if you find out this average, find out the average of this, the average of Vm sine omega t. So integrate from 0 to pi and you divide by pi.
2 by pi.
2 by pi.
2 Vm
By pi.
2 by
2 by
pi.
pi.
2 divided
2
by pi.
Vm by pi, sir.
So sine omega t, if you do sine omega t, what is the
636.
okay? Sine omega t, and then 2 Vm by pi. Okay.
divided by omega.
Huh?
So can you once again repeat the V average is equal to 1 by pi integral 0 to pi Vm sine omega t into dWt. What is that? dWt?
D omega t.
Differential of omega t.
X-axis
We are differentiating it with respect to
D
omega
omega t
t.
is actually differential of omega t.
differential of omega t. Okay, so you have to be very careful. Okay, I have taken the axis as omega t, not t. Okay, I have taken, so the angle, so the the full time period is from 0 to 2 pi. and half of the time period is 0 to pi. Okay, so I'm different. So there will be what will you do if it was sine omega t dt? What would be the integration?
0 to t by 2, sir.
Uh,
That is 0 to pi by omega.
no, if it is just sine omega t dt,
2Vm by pi omega.
omega. So, but here it is d
Sine-
omega t, so there will be no omega.
Yes, sir.
Okay, so you have to be very careful. Okay, so it is just integrating sine will give you minus cos. Integral of sine will give you minus cos. Okay, am I doing correct or wrong?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
So minus cos,
Yes, sir.
the limits are from 0 to pi. Hello? Call me later after 5 p.m. So the limits, so you all are experts in integration and all. Okay, but in this course you will also be needed to remember all those integration things. So you have to be very careful. I have done the integration with respect to omega t. So sine omega t d omega t is, it is just integral of sine theta d theta, which is basically minus cos theta, and you put the upper limit and lower limit 0 to pi, so it ultimately leads to 2 Vm by pi. So V average, so average value of this sinusoidal waveform, when we are doing the average over half of the cycle, is basically 2 Vm by pi, and if you have your calculator, you can find out what is the value of 2 by pi and all those things. Okay, 2 by pi times the maximum value of the waveform. Okay, that is clear? The average value.
Yes, sir. Yes, sir.
So you may be there may be a lot of questions on this average value if you just change the waveform instead of sine, if you are given some other shape. Okay, you'll have to basically you should be able to do the find out the average values. And obviously, if it is a symmetrical thing with both symmetrical positive and negative axes, then you know what to do. Okay. So the next thing is basically there is something called the effective values of sinusoid. So these terms you have to gradually master these terms. What is the meaning of this average value? The way it is defined. Now there is something called effective value. So what is the meaning of effective value of a sinusoid? So let us define just for convenience. There is nothing that why am I deviating from voltage to current? But let us define with respect to a current waveform. So although voltage could have been equally selected. Okay, so just instead of V equal to Vm sine omega t, I will assume I is equal to Im sine omega t or cos omega t. So that I will do for this, just for the sake of defining this. So the effective value of a periodic current is equal to the value of the direct current which flows through an R ohm resistor, delivers the same average power to the resistor as does the periodic current. So if you pass an periodic current through a resistor, okay, so this form, if you pass a periodic current through a resistor, okay, the amount of power that it gives should be equal to the power that will flow through it in case it is a DC current, direct current flows through it. So that is basically the effective value. So what is the power? What is the power through the resistor?
I square
RT. I square into R. Okay, but I square R is, but here I is itself a function of T. So it is basically I square, as soon as I write I square R, it is basically at a particular T. Okay, so to find out the total power, you have to basically find out this. You have to do this I square RT from 0 to T. This is the total power that is passing through this resistor for one full cycle, and its average value is the average power to the resistor. So this average value over this T To find out this average, you basically divide by 1 by t. So what you do is you do integration of I square r dt. You do integration I square r dt 0 to t, and then you divide by the t. So that is basically the average power going into this resistor if it is a periodic current. You see this word I have used here, periodic current, because it is I, which is a function of t. Now, if there is, so this is equal to you can do all these things. You just r is a constant, you can take it out. So it basically boils down to 0 to t I square dt. I have not yet written the it. As I have been telling, these are all functions of time, and we'll have to do a lot of calculations. So sometimes I will omit that t, but I is anyway a function of t, as you see in this figure.
Hello, sir.
Yes,
Sir, can't we make use of the V average we calculated in the previous slide?
that was average. You can do it, but that was these are different definitions. That was an average quantity.
So, sir,
And
here also we are doing the same only, no?
No, but here comes the concept of power. There it was just V dt. Okay, there it was just V dt.
So here
and
there is square.
Square, because square is coming. It is not that we are doing the square out of fancy. Okay, it is just to square will come
Sir, I was
whenever.
actually saying.
Yeah, square
I
will come when we
think
consider power. Okay, so
Okay, sir.
the square comes when we consider power. So that is how y square coming. So this is the average power consumed by this resistor over the one period. Now, if there is a DC current, DC circuit like this, the same resistance. Okay, so the same resistance, and there is connected a DC source, and it is some current is passing through it. You know it, how much current it is. You know how to handle a DC source. V by R equal to I. Now, for this DC source, also you can find out the current, the power. Okay, for this DC source also you can find out the power, which is I square R. So if this I square R is also equal to this total power that goes into the to the resistor in one full cycle, then what will be the value of this DC current that will lead to it? So that is how it is defined. So the effective value of any periodic current is equal to the value of the direct current which flows to that same R ohm resistor, delivers the same average power to the resistor as does the periodic current. So the amount of power the periodic current gives over one cycle, which DC current will give the same power. So that is basically called the effective value of the periodic quantity, in this case the periodic current. So in this case, what is the power? P equal to I effective square R.
I effective square R. Yes.
Square R. So what is this value of I effective? So that these two P's are the same. If you do this, so you get this I effective is equal to, if you equate these two P's, your R will cancel out. Okay, and what you are left with, I effective square equal to 1 by T integral of 0 to T I square dt. So I effective becomes basically the square root of 1 by T integral of 0 to T I square dt. So you see, to find out I effective, what you have to do is you have to find the integral of I square from 0 to T, then divide by T, and then taking the square root. Okay, so these are the steps. There are the three steps, because first you have to do the integration of the square. So given a periodic quantity, you have to do the integration of the square from 0 to T, then to average out. So you have to divide by T and then take the square root. So that is basically the I effective quantity of that periodic waveform. So in that case, this is how it is defined with respect to the current. Clear?
Yes, sir. Yes.
Yes, sir.
Hello.
Yes, sir.
আমি একটা ক্লাসে আছি, 5টা পরে কথা বলবো। পাঁচটা পর্যন্ত ক্লাস আছে। So this is the this is how our effective quantity is defined. Okay. So if you are given a certain I, you can find out the effective quantity by this: squaring the quantity, integrating it from 0 to t, dividing by t, and then taking the square root. So whatever is written in the formula is just written in the language. The effective value is obtained by squaring the time function, then taking the average value of the squared function over a period. So average value means doing the integration and then dividing by the t, and finally taking the square root of the average of the squared function. Okay, so whatever is written in this formula, I effective equal to root over 1 by t root integral 0 to t I squared dt is in the form of a language, that the effective value is obtained by squaring the time function, then taking the average value of the squared function over a period, and finally taking the square root of the average of the squared function. Okay. Any doubt on this?
No, sir.
So
Sir,
so this
I
is
effective
also,
is also called IRMS value.
so this is the thing. The next thing. So this operation involves finding the for finding the effective value is basically the square root of the mean square. So you basically have to do the square root of the mean of the square. Mean means 1 by t and square. So this effective value is often called root mean square value or simply the RMS value. Does it answer your question? So computing the effective value, it basically means finding out the square root of the mean of the square. Okay, so the effective value is often called the root mean square value or simply the RMS value.
Sir,
Yeah.
sir, here in the integral, capital T denotes time period, or it can be any time interval.
Whatever is the time period, you have to do by the same, divide by the same time, because we are doing the average. If you take it t by 2, then you divide by t by 2, 1 by t by 2.
Okay, sir.
Okay, because you have to do that 1 by t is for averaging out the square.
Yes, we are averaging it out over one time period, complete time period. So we are taking t in this case.
T. If you choose
Yes.
some other time, then it will be
Then we
accordingly.
get other time. Yes, yes.
Yeah. So you understand. So this is also called the root mean square value. That is root of the mean of the square. Okay, that mean means what? 1 by t. 1 by t is doing the mean. Okay, so you know how to do mean. If you have 10 numbers, you know that you have to do, if you have 10 numbers x1, x2 to x10, so you know that x1 x plus x2 plus x3 plus x4 plus up to x10, and then divide by 10. So that is the mean. So here also you are doing the integration up to the time t. You have to divide by the t. So it is called the root mean square value or simply the RMS value. Okay, so does it answer the question? Somebody asked about this root mean square. Okay, so this is also called, so the effective value is also called the RMS value. Okay, any question?
No, sir.
No, sir.
Yeah, so you know, so deliberately I had kept some gap in the title here. You just see the title, effective values. So the reason is this. So it is basically the effective or RMS values of sinusoids. It is also called, sometimes in some books you may find effective value, RMS value, you know, they both may be interchangeably used. So it is also called effective value. It is something, the same quantity is also called the RMS value. So these things should be clear to you. What is the meaning of effective value? What is the meaning of RMS value? They are same, but it is different from what is called the average value. But this is how it is defined: the effective value or RMS value of a sinusoidal quantity. So let us do one example. Like if you are asked to find out the effective value or say the RMS value of a sinusoidal waveform, and you are given this IT equal to Im cos omega t minus theta. So this is the equation of IT that we were seeing, that if you apply Vt equal to Vm cos omega t, that will lead to IT equal to Im cos omega t minus theta, obviously assuming an RL circuit. And RL circuit is a very common circuit, because anywhere you take, you know, as soon as the wire is put in the form of a coil, it will result in an inductance L. And as soon as there is an inductance, it will lead to an angle minus theta. So the current will lag the voltage by an angle theta, which you can compute. Theta equal to tan inverse omega L by R. So you have to be very much handy in using the calculator now, because more and more now usage of the calculators will start. Is there anybody in the class who does not have a calculator?
Yes, sir. I don't have.
Huh?
Yes.
What is the name?
Yes, sir. I am also.
Anik.
Aniket, you need a calculator now.
I don't have.
Now you need a calculator. The test is declared, and anywhere, any such calculation has to be done by calculator. Otherwise, you will struggle. You will not get the end. No, calculator, a scientific calculator. You are now going to be engineers. In whatever domain you are, now you have to do calculation, and you cannot tell I don't have a calculator. And all the tests are being
Okay,
declared. You have to soon buy a calculator, and scientific calculator. You ask your seniors or somebody else what type of calculator is required, because a lot of these things will come now: multiplication, division, addition, cos theta,
Scientific
sin.
non-programmable calculator.
Scientific non-programmable calculator. Yes.
Sir, I have to ask something in this regard. In the last class, our TA said we can do the like solving the equations and the complex analysis in the calculator itself. Is it permitted?
Yeah, if it is, the question, like, when we used to use calculator, all these features were not there. Okay, but right now, these days, something is there in the calculator, but you can do that ultimately, but there will be many other things you have to do in the copy. So this
So
final
like in
calculation.
the class we had an equation.
So the thing is that there are some calculations, there are many types of scientific calculators. So there are some calculator like the FX82MS, where we can only do the basic scientific calculations, and there are some like the FX991MS, where we can do integration, differentiation, solving matrix, solving equations
No,
in three variables.
that will not be allowed. That will not be allowed. That FX 82C or 82D, whatever you are telling, then those type of things will be allowed. Just maybe computing some matrix or determinant may be allowed, but not beyond that. Okay, find out the RMS value of this. Find out the RMS value of this. Suppose this has a period of period of t, so your omega equal to 2 pi by t, so t is equal to 2 pi by omega.
Find out by root 2, sir.
Yes,
Yeah,
I am by root 2.
Yes, sir.
So
By root 2.
So this is basically
I
the
am by root 2.
effective value formula. We just now did. IRMS equal to root over 1 by t, integral of 0 to t, capital T, Im square cos square omega t minus theta. This is the thing that is being given to you. It is Im cos omega t minus theta. So you just directly substitute there, and so you get basically I square t dt, which gives Im square cos square omega t minus theta. Okay, so cos square omega theta. So how will you do the integration? So cos square theta will be converted to
Cos
1
2
plus
theta.
cos 2 theta by 2.
1 plus
Cos 2 theta by 2.
1 plus cos 2 theta by 2.
Yes,
Okay,
sir.
so it basically comes to 1 plus cos 2 theta by 2. So substituting this t by 2 pi by omega, so basically you do the integration from 0 to 2 pi by omega, and this Im square goes out of the square root as Im, and so you are left with this 1 by 2 plus 1 by 2 cos 2 omega t minus 2 theta. So that is 1 plus cos 2 theta by 2 into dt. So when you do this integration, so the integration of a cos over the whole cycle will give you what?
0.
0. Okay.
Zero.
So you ultimately get this Im omega by 4 pi, because this 1 by 2, this 1 by 2 will go with the denominator, so that is 4 pi. So that is omega by 4 pi, and the integral of dt, which is t, 0 to 2 pi by omega. Okay, so this you have to be very much conversant with all these integration things, correctly applying the formula. I hope you will all do it, because you are just fresh from this trigonometry and all. Okay, so but all these formulas have to be correctly remembered and implemented. Okay, because in many of the places you may have to actually do these integrations and all, and then if your basics of trigonometry are wrong, then you will keep on getting wrong answers. And all this change of variables and all. So ultimately it leads to Im by root 2. And if you have a calculator, as somebody must have calculator, just find out what is the meaning of, what is the value of 1 by root 2.
0.707.
0.707. So this is a very favorite value. 1 by root 2 is 0.707 Im. So you see the effective value. Effective value is basically the DC value. Okay, the effective value has become equal to 0.707 times the magnitude of Im. 0.707 times the magnitude of Im. Okay, all of you have got this?
Yes.
Yes, sir.
Yes, sir.
Yeah. So just check this. I'll just take 1 minute break. I'll just have to have water. Yeah. So this is the effective value. For if it is a sinusoidal wave, if you have a sine, you can also check that you will get the same thing. So if you have a sinusoidal, the effective value is basically 1 by root 2 times the maximum value, or 1 by root 2 is 0.0707, the maximum value. So the effective value of a sinusoidal quantity is basically a real quantity which is independent of the phase angle and numerically equal to 0.707 times the amplitude of the current. So whatever is written there in mathematics is just written in the form of a language. The effective value, it is basically a real quantity and its magnitude is, which is numerically equal to 0.707 times the amplitude of the current. Okay. Magnitude of the current. So what is the value of Im? Im becomes root 2. Im becomes what? Root 2 I effective. So Im becomes root 2 I effective. So a current of root 2 cos omega t minus theta. So we'll basically have an effective value of 1 ampere. And we'll deliver the same average power to a resistor as will a direct current of 1 ampere. Okay, so you understand this statement? So a current of just,
Yes, sir.
okay, a root 2 times cos omega t minus theta, if that is your alternating current, it will give an effective value of 1 ampere and it will deliver the same amount of power to any resistor due to a direct current of 1 ampere. A direct current of 1 ampere will give whatever amount of power. Okay, an AC quantity of root 2 cos omega t minus theta will give the same amount of power in over one cycle. Okay, so that is the concept of effective value. Yes.
Sir, is this the definition of 1 ampere?
Which one?
Sir,
No,
the last...
this is not how ampere is defined. Ampere current will be defined with respect to you. You better know how currents are defined. That is how much amount of charge flowing through per second and all. Okay. So this is just to compare between the effective value and average value. Okay.
Okay, sir.
Yes,
So
sir.
now there is another definition which is called form factor. Okay, so these are some of the definitions that will be coming. The more and more you do advanced electrical engineering, advanced machines, and all, the relation between the different types of waveforms. So form factor is defined by RMS value by average value. Okay, if you are given Im cos omega t, your RMS value is 0.707 Im, and you know what is the value of average. So you can find out what is the form factor of that waveform. If you are given a periodic waveform, the form factor of that waveform is given by RMS value by average value. Okay, so we will this type of these definitions. There are many other factors also in electrical engineering, but this is one of the basic factors that relate the average value and RMS value.
So this average is half cycle average value, right?
Yeah, obviously. Otherwise, you take the full cycle, the denominator becomes what?
No, sir, I mean the form may not be sinusoidal always. So
Yeah, if it is a sinusoidal, obviously you have to take the half cycle average.
okay.
So then we have to consider the effective value of the current, or the quantity that we are measuring also in the half cycle, or that would be in the full cycle.
That you check whether they are same or different.
Okay, sir. Sorry.
Sir, of what?
No, there is
Sir,
nothing to be
what
sorry.
means
Who is that person who told sorry?
Sir, I am Anubhav Mondal.
Anuva, whatever it is, there is nothing to be sorry. It is all mathematics going on. You can check. It is better to check if it is something
Yes, sir, I
different. Or
didn't check it. Yes.
No, you check it. You do it at your homework. Everything may not be possible in the class. Whatever queries you are having, better check it mathematically. Because it is all mathematics going on. Trigonometry, integration, square root, multiplication, division. So you take your calculator and whatever you are thinking, think in the mathematical point of view and see whether they are coming same or different. If they are different, why? If they are same, why? Just think about it. Okay, there is nothing to be sorry.
So it
Anyway,
will be same because on
Ah.
squaring the
What
time
is-
period becomes pi
Yes.
from 2
yeah.
pi.
But you have to be very careful about the limits. Okay, because you are dividing by 1 by t. In that case, it will be t by
Yes,
2. The integration limit will be t by 2, and then you see whether it leads to the same value or different value. So many things are obvious, but obviously you have to check it mathematically also. Does it answer your
Sir,
my question?
what?
Anubhav?
Yes, sir.
Hmm.
Yes, sir. I got it.
Yeah.
Yes.
Sir, what is the use of this form factor?
We will.
Yes, sir, that is
So this is as I told. There are many factors in electrical engineering. Okay, this factor we will see when we will. I think it will come in your curriculum when we teach transformers. Okay, it is just for the sake of a definition. That is a particular waveform. If it is sinusoidal waveform, it has a particular form factor. Okay, if it is some other waveform, it will have some other waveform. So that is how it is defined. Form factor of a waveform. Okay, and we will use this form factor. Hello.
So basically, form factor is the signature of a particular kind of waveform.
Yeah, a particular type of waveform will have a particular type of form factor. And we will. I think it will come in your when we teach transformers. It will come in the formulation. Some in some formula it will come, and actually those of you who will be teaching, who will be studying electrical engineering, it also comes when when you have to actually design transformers. Okay, so transformer design, or all these electrical machines that you see have to be designed. So electrical machine design is a subject in itself, and it is a very interesting subject. And because you will have to, given a particular specification, you will have to design a transformer. Okay, so which will actually come in your those in the electrical machine second year, third year curriculum. And you can even, you may have to even design transformer on your own if you are doing some project like that. Okay. So transformer, suppose you develop some robot in your lab, and some small robot, so that will have to handle certain amount of power, for which there may be requirement of a transformer. Then that transformer may not be exactly available in the market. You may have to make it a custom transformer. So in that case, in all this, you'll actually have to do transformer design. So the first transformer design has to be done in pen and paper, and then you have to, these days a lot of software is there where you can actually design it in software and see how it is going to behave, and then you have to actually fabricate it in the lab. Okay, so those of you, some of you may sometimes in future, if you take up some project where there is a requirement of transformer design, then many other factors will be there. You'll have to basically read some book on machine design where such factors will be coming. Okay.
Okay, sir, got it. Thank you.
Yeah.
Yes,
So
sir.
actually, this reminds me of one of my students who graduated maybe 10 years ago. Actually, yeah, 2010, 11. Yeah. in his BTech project, all of you know BTech project, no? You have to do a BTech project in your 4th year. So he did a work on a robotics application, and he actually designed the transformer. He designed the transformer in the lab, first theoretically and then in software, and ultimately he made it in the lab also. So for such cases, you will have to. There are many other factors. So form factor is one of them. So right now you have to basically remember it, know how how it is defined, and somewhere it will come. Okay. Can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So now we will come to something else. So that was all about the different waveforms. AC waveform we introduced. We defined the effective value. We defined the average value. Effective value is also called RMS value, and we also gave the notion of the phasors as we put the different circuit elements along with R. If we put L, we saw that the currents lag the voltage and so on. So gradually we will be going deeper into this actually. So now the forced response by a sinusoidal function means we have done this, that if you have a network, N, and if you put some alternating quantity into the network, okay, and so obviously that is a network is meaningless without any voltage source. Okay, just a mesh of wires means nothing, because until unless you charge it. So if you put an alternating source Vm cos omega t plus theta, okay, so what it will generate? It will also generate a current. In some particular branch there will be a current, and the current will be of this form Im cos omega t plus phi. So what we have done is I have just introduced some arbitrary phase theta into the voltage waveform, and in the current will also have a different phase. Okay, until unless it is a purely resistive circuit. Okay, until unless it is a purely resistive circuit, the voltages and current phases will be different. Okay, if they will not align in the phasor diagram. Is it clear?
So
Yes,
will you
sir.
repeat
Yes.
what you said just right now?
Uh-huh.
So will you repeat once what you said just right now?
Okay, so
That-
the repeating is until unless this network is a purely resistive network, the voltage phasor and current phasor will not align.
Yes.
Okay, so earlier I had kept Vm cos omega t, and it was cos omega t minus theta. But suppose the voltage waveform is Vm cos omega t plus theta, then Im is Im cos omega t plus phi. These two angles are actually different. Will be different. If they are equal, it will be a very special case. Okay. So a sinusoidal forcing function. So Vm cos omega t is basically the forcing function. It will always produce a sinusoidal forced response of the same frequency. Okay, so we are not considering the cases that there can be some other frequency and all. Okay. So if there is a sinusoidal forcing function, it will also produce a sinusoidal forced response of the same frequency. That is, omega is the same. Okay, so we saw that for that RL, if we give Vm sin omega t, we got Vm sin omega t minus theta. So that omega was the same. So the forcing function, a sinusoidal forcing function, always produces a sinusoidal response of the same frequency. Now, if you shift this frequency by 90 degree, if you shift the frequency phase of the forcing frequency by 90 degree means what? If we do it this, Vm cos omega t plus theta minus 90 degree. So just I am shifting it. What will it lead to?
Sir,
So
sin.
90 degree behind of Im.
Sir, sin.
So cos omega t plus theta minus 90 degree means what? I am just
Sin omega t.
sin omega t.
I am just rotating the phasor. Okay. As soon as I do cos omega t plus theta minus 90 degree, I am just rotating the phasor, the forcing function. Okay. It was earlier at plus theta, then I have done minus 90 degree. That means I have just rotated the phasor. So, but what will it lead to in the response? In the response, what will happen?
There will be a lag of 9.
Lag of
Again, the response will also lag because both the voltage and current phasor will having the same relative spacing. Okay, so if you change the forcing function to this, so this basically gives you Vm sine omega t plus theta.
Yes, sir.
So what we have done is we have done this. We have fed with this Vm sine omega t plus theta. So what will be the response? What will be the response?
Im sin omega
I
t
am
plus
cos
phi.
sin omega t plus phi.
So the response will be I omega t plus phi. Yeah. Okay. So you see, just we are doing mathematics. Okay. We have the Vm cos omega t plus theta. We shifted that, so we will also get the same response. You can do it. In the same example that we did in the RL circuit, if you just instead of sine or cos, you will interchange it, you will get a similar term. So what does this lead to? So if you put sine omega t plus theta, Vm sine omega t plus theta, it will lead to an Im sine omega t plus phi. So it will generate a corresponding response. If you put a sine wave as input, your output will also be a sine wave. If your input is a cos wave, your output is a cos wave. So how do you get this? I am sine omega t plus phi. So this is basically this. I am cos omega t plus phi minus 90 degree, which will be equal to I am sine omega t plus phi.
So
Clear?
how does the frequency does not change of the output?
Because it is you saw in the RL circuit. Did it change in the RL circuit?
No, sir.
So we will, for the time being, we will assume these circuits only in this curriculum, that any frequency change and all will not be considered.
Okay,
So
sir.
this type of RL and C elements, you will also find mathematically it does not change.
Okay, sir.
Okay, so these are basically called the linear elements. Okay, so here it will not change. For some other advanced course, you may have to encounter different other situations. Is it clear?
Yes, sir.
Yes, sir.
Okay, so so what we did was we just put just 1 minute, my computer is hanging. Vm cos omega t, it generated Im cos omega t. If you put sine, then it also generates sine. Can you see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, you have to wait.
Yes, sir.
Yeah. Now I think it is working. My screen is visible?
Yes,
Yes, sir. But same
Yeah.
slide. Have you
The
changed the
previous
slides?
slide is visible.
No, I'm not. Now I'm changing now.
The full slide is
So now can you see it?
So the
Slide
same
11?
slide.
Yes, sir.
Sir, the same
Same
slide.
slide.
you can see.
These
Same
are same
slide.
slide.
Previous slide.
Slide is not changing. Yes, sir. Slide has not changed.
What is the slide now?
Forced response of to sinusoidal function.
Post response to sinusoidal
Page number
function.
10, sir.
Yes, sir.
Not
Now
in
change.
Yeah, now
Not
it's
changed.
changed.
Yes, sir. Now it has changed.
It is 11.
Imaginary sources.
So if I consider like this, there is the same network. Now earlier it was Vm sine omega t plus theta. Now I just do a multiplication by j. What is the meaning of j?
Root
J,
minus 1.
yeah, it is the same as the root over minus 1, that is the equivalent of imaginary quantity. So this will lead to what? This will also lead to j Im sine omega t plus phi. Mathematically it will be true if I put it by j, multiply it by j, so that if you solve the differential equation.
Sir, here
Okay.
j is the root over minus 1.
Sir,
Yes.
what is J?
J is root over minus 1, as somebody told, So if we just multiply by j in that differential equation, ultimately we'll get this type of current also.
Sir, J means under.
Sir, what is the meaning of multiplying iota?
Iota?
Means
Under
root
root
minus.
is equal to iota, sir.
Huh? Where is iota?
By iota he means root under minus 1.
So that we will see, that we will see, but okay, that we will see, but mathematically just you have to appreciate that we have done this. Okay, so if this is the forcing function, and then you put in that equation, and then you will get this type of response. We'll see why I am doing this. Okay.
Sir, J means
J means root over of minus 1, the imaginary quantity. Is it clear?
okay, sir.
Okay, so now if we sum these forcing functions, if we sum this Vm cos omega t, earlier we were doing, and now if we sum J Vm sin omega t, what is the meaning of this?
E raised to I omega t plus
Real
theta.
and imaginary parts.
Cos theta plus j sin theta is e to the power j theta.
Vm e to the power j theta.
Vm
So,
is the power of omega.
so if we put this as the forcing function, Vm cos omega t plus j Vm sin omega t, so that means it will also produce a response like this. Im cos omega t plus j Im sin omega t plus phi. Okay.
Yes, sir.
Yes, sir.
So this source may be written as Vm e to the power j omega t plus theta. As soon as we combine, so just for representation, cos omega t plus theta plus j Vm sin omega t plus theta, so it becomes equal to Vm e to the power j omega t plus theta. So if this is the source, so this will lead to a response of what type? Im e to the power j omega t plus phi,
Theta.
and Im e to the power j omega t plus phi. So theta is associated with the source, and the response is associated with phi. The source maybe is Vm e to the power j omega t plus theta, and the response is Im e to the power j omega t plus phi. Okay.
Sir, why do we use J instead of I in electrical engineering?
I represents current.
Yeah, yeah, that is also correct. I represent current. Okay, so J, yeah, interesting question, but that can be one answer. Okay, so J is nothing but root over of minus 1. Whatever I you have used in your, plus 2, it is basically the same quantity, but
While reading this AC chapter, I read this only, that the reason for not using I was this.
yeah, very good reason. Yeah.
Yes, sir. Same reason.
Yeah, so the source may be written as, so if you put this, so what you just understand what the sequence I am following. Earlier we were used to giving cos, we got the cos response. If we put sine, we got the sine response. If you multiply by j, so they will get this response. So you have to basically solve the same differential equation. So now if you combine them, you will get this type of combined response. Now this combination you can write it in the form Vm e to the power j omega t plus theta. you know cos theta plus j sin theta is what? You know, you have been doing it. So it is a to the power j theta and you get this. And the response can also be combined as Im e to the power j omega t plus phi. So basically, if you see that if there is a network and if you give this as the input, then you will get the response like this. Giving as input Vm cos omega t plus theta plus j Vm sin cos omega sin omega t plus theta is the same as telling that we are giving an input Vm e to the power j omega t plus theta, which will lead to Im e to the power j omega t plus phi. Okay. So we actually can make this statement that a real and imaginary or a complex forcing function will produce a real and imaginary or a complex response. Okay.
Yes, sir.
So we will soon realize why I am doing this. See, what was our initial forcing function?
Vm cos omega t plus theta.
Vm cos omega t plus theta. Very nice. So Vm cos omega t plus theta is what?
Real forcing.
Real part of this.
Yes, sir.
Real part of this. Similarly, our response was Im
Cos omega t plus phi.
phi. So basically the real part of this.
Yes,
Okay.
sir.
So, but if we consider this input in this form, exponential form, basically the real value is actually fed when we feed to the network. Okay. In the network, we actually we feed the real value, cos omega t plus theta. That is the way we have assumed. Okay.
Yes, sir.
Yeah. So the writing, the point of writing in this exponential form will have some computational advantages that we'll see right shortly. So what we are doing is our cos omega t is nothing but real part of e to the power j omega t. Cos omega t is all of you know. All of you have experts in this. Okay, trigonometry and imaginary numbers and all. So cos omega t is equal to real part of e to the power j omega t. But here we will make a usage of this, which you will see that help in our computation. So cos omega t, which is basically the necessary complex source, e to the Vm e to the power j omega t. Our complex source was Vm cos omega t. So which is nothing but Vm real part of e to the power j omega t. Okay.
Yes, sir.
Yes, sir.
And the complex response is complex response was Im e to the power j omega t plus theta.
So it was plus phi.
Plus phi, but see here I in the source I have kept a phase as 0.
Oh, sir, okay.
Okay. So you will see. Okay, you don't mix up, but you have to concept should be clear. Okay. In fact, earlier it was minus theta in my initial. If it is an RL circuit, the angle theta is basically negative.
Yes.
Okay. So should not try to confuse. So what we are actually doing is, if we have an RL circuit, and if we are giving this, in our RL circuit we are giving this Vm real part of e to the power j omega t. We are giving e to the cos omega t. The cos omega t giving means it is basically real part of e to the power j omega t. Okay.
Yes, sir.
So this will actually lead to.
Yes, sir.
This will actually lead to real part of Im e to the power j omega t plus theta.
Yes, sir.
Okay. So if we put this in because ultimately we have to get the expression of this. So if you write the differential equation, so this was the differential equation. Ri plus L di dt equal to Vs. Okay, so if you put in this differential equation, you get this. In the left hand side, Ri. So Ri means Rim real part of e to the power j omega t plus theta. If you put this I here, it becomes RIM, real part of e to the power j omega t plus theta. Just substitute it here. Then for this L di dt, what will we get? We will get LIM, then j omega, derivative with respect to t, so you will get j omega coming out. Okay?
Yes.
J omega coming out, so get real e to the power j omega t plus theta. And Vs is equal to Vm real e to the power j omega t plus j omega t. Okay.
Yes, sir.
Now if we see since this is real, we just remove this real. Both in the left hand side and the right hand side, it is so we basically get this type of equation. R plus j omega L Im e to the power j omega t plus theta and Vm e to the power j omega t. And from here, what do you get? See, you see,
So can
So
we
we can
cut
get the
j
complex.
omega t?
Yes, sir. We can
Huh?
get the complex amplitude of Im, like
Yes.
Im tilde.
Okay, so your Im e to the power j omega t, e to the power, sorry, Im e to the power j theta. Your Im e to the power j theta. See, ultimately the objective was to find out IT. And out of IT, e to the power j omega t is anyway there. What is required is Im e to the power j theta is required in this IT expression. So Im e to the power j theta is Vm, the magnitude of the voltage, by R plus j omega L. All this you know, R you know, L you know, omega you know, as soon as the waveform is defined. So Im e to the power j theta is nothing but Vm by R plus j omega L, which you can rationalize the denominator and you get in this form. So you have a real part, and you have a imaginary part. And you know why I did like this, the dividing the denominator. Because from the second part, what will you get? It will be in the form e to the power j theta. Okay, so from this, what you get? Your Im is basically equal to Vm by root over R square plus omega square L square. Im equal to root over Vm by root over R square plus omega square L square.
Yes.
Okay. So Im e to the power j theta is Vm by root over and e to the power minus j phi. What is cos phi equal to? So this is equal to cos phi plus j.
Sir, cos phi is equal to R upon under root R square plus omega square L square.
So cos phi is equal to Vm by Im into root R square plus omega square L square into cos phi.
Hello, sir.
Sir, you are not audible. Sir, you're not audible.
Can you see my screen?
No, sir.
Yes, sir.
Yes, sir. Yes, sir. We can.
Yes, sir. Yes, sir.
Yes, sir. Your screen
Yes,
is
sir.
visible.
Yeah, we lost the signal for some time. So what was the what is the cos phi here?
Sir, R upon
Sir,
under root
I
R square
am
plus omega
into
square L square.
root R square.
And
I
sin
am
phi?
into root R square plus omega square L square
Sin
upon
phi
Vm.
omega L upon
And
under
sin
root
phi?
R square omega square L square.
Omega L by root over R
Minus
square
omega L.
minus omega L. Okay.
Omega.
So,
Yes, sir.
एक minute, there is some problem with my computer again. Can you see the screen?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Can you see now?
Yes, sir.
We are seeing the same page, page number 12.
Okay, okay.
Yes, sir.
Screen is black now.
Now?
So it's stuck on the same. Yes, sir, it's visible,
Page
but it's
number-
stuck on the same page.
No, that is the same page, you know. That is the it is not going forward or backward. You have to wait. So it's clear now? Now you can see I am equal to this. Can you see?
Yes, sir.
Yes, sir. We can see, but it's the same page.
Okay, whatever it is, I have not gone to the
It is the
different page.
same page as that of before.
Okay, no problem.
You can see this I am equal to Vm by this. This
Yes.
first part is basically I am.
Yes, sir. Yes, sir.
And
Yes,
cos,
sir.
cos
Yes,
phi
yes.
is R by this. And sin phi is basically omega L by root over R square plus omega square L square. So
Minus.
Sir, there should be minus omega L.
minus omega L, if you take cos theta minus j sin theta.
Phi equal to minus
E
omega.
to power minus j phi.
Yes, there should be a minus.
No, sir, it's fine. Minus phi
Yes,
has
it is written on the minus
Okay,
j.
okay, it is
minus phi has been taken.
It is all right.
e to the power
Yes,
minus.
minus. Yes, it is right.
Yes, sir, I did not understand
sir, it
why
is.
there is not minus.
Cos theta minus j sin theta is what?
E raised to power minus theta.
Because in previous point it is written that e to the power minus j theta. Here minus theta is e to the power minus j phi. Here minus phi is written. We are only writing about phi.
Yes, the minus is adjusted.
Okay, so
Yes, sir, got it, sir.
so you see that what we are actually doing is we have we are solving this equation algebraically. So we are solving this, so writing this in this form. The advantage is we are doing it algebraically instead of solving a differential equation, directly solving a differential equation. Okay?
Sir, you cancelled the real part now here in the writing the differential equation below that. Is that a trick or is that a valid operation?
Which one?
Below the writing the differential equation, you cancel the real part, no? So is that a trick or valid operation?
That is a valid operation. Yeah? What we have done is the Vm cos omega t, which was our input, we have written in the form Vm real part of e to the power j omega t, and whose response is also the real part of Im e to the power j omega t plus phi plus theta. Substituting this, and ultimately we'll get this solution. It equal to Vm by root over r square plus omega square L square cos omega t minus phi, which we were getting earlier also, but solving the differential equation. Okay.
Yes, sir.
So the advantage is we are solving an algebraic equation, which may be easier in some places. Handling algebraic equation, handling complex numbers rather than solving differential integral equations. Those are removed, and we will also study this later. So suppose you are given a numerical, find the complex voltage across a series combination of 500 ohm resistor and a 500 millihenry inductor. The complex current is, you are given the complex current 8 e to the power j 3000 t milliampere. So that omega is basically 3000. Okay, so 8 e to the power j 3000 t milliampere. So find the complex voltage. Okay, so let us assume some complex voltage. Obviously it will have the same frequency. It will be having Vs will be of the form Vm e to the power j 3000 t plus phi. Okay, there will be some phi generated because it is an RL circuit. So what is the unknown here?
Phi, sir.
Only phi.
And Vm.
Yeah,
VM also.
find them. So that is the complex voltage to be found out. So you have Ri plus L di dt equal to Vs. Okay, so directly putting in the differential equation, to find the value of Vm and phi. Who has found out?
Sir, is phi 29.68 degrees? Plus
Phi is 29.68, yes. And Vs and Vm?
4.
Fine.
4.
So 46 into 10 to the power 3.
40?
6 into 10 to the power 3. 46 into 10 to the power 3.
I don't think so. So you are basically writing this.
So 67.5?
67.5. What? So this is the thing. See, Vs plus Ri plus L di dt. You have to be very careful about the units. R is 500 ohms. Current is in milliampere. Okay, so 8 into e to the power j. So that will be multiplied by 10 to the power minus 3.
So 2.3 ampere current. 2.3 volt. Vm equal to.
No.
So Vm is equal to 456.5. Sorry, 4565. 4565.0.
4.6. Yes, sir.
So that type of thing. 4.6. You see, your L is 95 millihenry. So it is 95 10 to the power minus 3. So it comes to this 0.095 into then ddt of this current. Obviously it is in milliampere, so 8 will be not 8, it will be 0.008 e to the power j 3000 t. If you do this, you basically get this e to the power okay. Can you see my screen?
Yes, sir.
Yes, yes.
Yes.
Yeah. So now you know what is the again my screen is hanging.
Sir, can we direct use Vm equal to Im into Z?
You can do many things, but I have not yet introduced Z in the course. Okay. So the purpose of doing this example is just to directly doing it algebraically rather than solving a differential equation.
Sir,
Hmm.
sir, in case of an LCR circuit, when we write the impedance as I mean Z, there we write. So in case of an RL circuit, also we can define that I mean under root of R square plus omega L whole square as Z impedance.
You can do many things. What is your name?
Sir, Anubhav.
Anubhav, but I have not used the word impedance yet in the course.
Yes, sir. I mean, just
Okay,
asking,
so
sir, because we
no,
learned in the.
you should not ask me something which I have not told yet.
Okay, sir. Sorry.
When I was doing DC, I was not entertaining any AC questions. Okay,
Yes, sir.
so that is the thing. So
Yes, sir.
so now from here you can find out the value of my computer is disturbing. I don't know what to do. So you get this. So from here you can find out this VM is 4.6 and phi is 29 point. So as soon as you get this 4 plus j 2.28, so it is, you can find the magnitude, you can find the angle. So all of you should have calculators. This type of imaginary numbers now you have to handle. Finding the magnitude, finding the tan inverse and all will be required. So this is the VS. Okay.
Sir, is the Vm in volt or kilovolt?
You tell me.
It's coming in kilovolt.
Anybody else got kilovolt?
No, sir.
Yes,
It
sir.
is
No,
not
so
volt.
actually the current is
Yes,
in
sir.
milliampere. Current
Huh?
is in
Sir,
milliampere.
current is in milliampere.
Huh.
Current is milliampere, so it would be in volt.
Milliampere. I have multiplied by 10 to the power minus 3 everywhere.
Okay, sir, got it.
No, but you have to be convinced whether it is kilovolts or something. But
No, I did not see the milliampere.
so you need to, milliampere you did not see. Okay, then you will make a lot of mistakes.
Yes, sorry, sir.
It is clearly nothing. Sorry, it is. You will lose credit. It is clearly typed in the question. You have to read the question properly.
Yes, sir.
Okay. So next thing is the phasors. So we have done this, that if the voltage input to a network is Vm cos omega t plus theta, then there is a corresponding output which is in the form of a current to some branch Im cos omega t plus phi. Okay, so this can be your typically some voltage equation. Now see, what we have been telling this is both the voltage and current are of the same frequency. It is of the omega t. Okay, omega is the same for both. Okay. Now voltage is at a certain angle theta and the current is at a certain angle phi. Okay, the current is at a certain angle phi. Okay. Hello, can you hear me?
Yes.
Yes, sir.
Yeah. So
Yes, sir.
you see, when we represent phasors, it is just sufficient to remember what? It is just sufficient to remember the magnitude as well as this phase, because both are having the same omega. Okay. So the phasors are represented by this form Vm angle theta. So Vm angle theta. So this is the notation. We will be soon using this notation. Vm angle theta means Vm cos omega t plus theta. There is an omega, it is obvious because it is an AC quantity, and there is some sinusoidal quantity, and if we assume cos, it is cos. Similarly, the current will be represented by this Im angle phi. If it is Vm angle theta, then it is Im angle phi. Okay? All of you are clear?
Yes, sir. Yes.
Yes, sir.
Okay, so this is just a representation. Vm angle theta, it means Vm cos omega t plus theta. Okay, and we have seen how this also can be represented. Cos omega t plus theta can be written as e to the power j omega t plus theta, real part of e to the power j omega t plus theta. But at the end of the day, the AC input that is going is Vm cos omega t plus theta, which is producing an current Im cos omega t plus phi. And these since a lot of mathematics have to be done, we'll have to adopt some notation. So, and it is sufficient to remember only the magnitude and the phase. Okay. It is sufficient to remember only the magnitude and phase. Okay, so it is sufficient to remember the magnitude and phase. Okay. Clear?
Yes, sir.
Yes.
So we do this type of notation. So Vt is equal to Vm cos omega t can be written in Vm angle 0 because there is no phase. Okay. Similarly, for an RL circuit, we got this It equal to Im cos omega t plus phi, which can be written as Im angle phi.
Im angle. Yes.
Okay, so you understand the meaning. So if I write Vm angle 0, it means Vm cos omega t because the angle associated is 0. Similarly, It.
So if the function is of sine, then we will convert it into cos, and then we'll write this in form, now. Or it is also for sine.
You follow anything. If you follow cos, you do cos consistently. If you follow sine, you follow sine consistently. Okay.
Okay, sir.
Now, so what does it mean? So if your Vm is here and your Im is somewhere here, is a representation. Now this phi can be positive, negative depending upon the situations, but we have assumed okay some phi, positive phi. Is okay this general notation? We have been doing several times.
Yes, sir.
Yes, sir.
And also VT and IT are of different magnitude. You see that I have kept the phasor lengths different. IT can again be bigger than VT magnitude wise if the denominator is less. But suppose the denominator is greater, it will have a lesser value. Okay?
Yes, sir.
Okay. So suppose you have this just a pure resistive circuit. VT equal to IRT. So what is the phasor?
So they will be in the same.
Sir, they will be
They will be in the
coincident
same.
on the same
Both
reference.
coinciding. So okay, VT is along the reference. IT is also along the reference.
Along the reference. Yes.
Okay, so VT, IT, they are, I've tried to give by different colors, but since they are overlapping, though they are of different colors, they can be identified by their arrowheads. Okay. Now, if you have a pure inductor, okay, your IT, suppose, and you are given IT equal to Im cos omega t, which is equal to Im angle 0. Okay. Hello.
Yes, sir.
Yes, sir.
Yes,
So
sir.
now find out VT for this.
VM angle 90.
So how to find out? So VT is
VM
basically
angle 90.
L di dt.
So
Minus.
VM minus 90. Angle
No,
90. Minus 90.
yeah, but you have to find out mathematically. VT is L di dt, and IT is Im cos omega t, which will give you cos differentiation will give you
Minus
sine,
sine
minus
omega
sine.
t.
Okay.
Minus sine.
You have to recollect all the differentiation integration correctly. So it is L Im minus L Im omega cos sine omega t. So this minus sine is equivalent to cos omega t plus pi by 2.
Yes, sir.
Okay.
Excuse me, sir.
Yeah.
Sir, but when we go along the current, then we take minus L di by dt, na? Sir, then here the last thing will change.
Yes, sir.
Which one?
Yes, sir.
Sir,
The
when we
voltage
go
is
along the current, then we'll take minus L di by dt. Then the last part will change. That is omega L Im into cos omega t plus pi by 2. Here,
No,
uh,
I have written this VT. That is the driving voltage is L di dt, the voltage across the inductor. Okay, that minus plus will appear because of the it opposes the cos, but magnitude wise it is L di dt.
yes, sir.
Are we
So
considering only magnitudes?
yeah.
But then it can change the phase difference.
Yes, sir. In last equation there will be change because in the second step we will not get minus.
Which one? If you differentiate this cos, you will get minus. It is coming out of the differentiation.
Yes, it is because of differentiation. So that initially, if we have minus L di by dt, then the minus will get cancelled.
No, we are not initially keeping because this is the voltage across the. I'm concerned about the voltage. Yeah.
Sir, even if we write KVL, we have to write like this: V minus L di by dt equal to 0. So if we
0. Yes.
bring that to right side, it will
Yeah.
be positive.
Hmm.
So it will turn out to be the same.
Yes. So you see, your VT is having a magnitude omega L Im. So whatever was the current magnitude Im, okay, your VT magnitude is Im multiplied by omega and L, and you see the phase. So your VT is, if you write in this form, the magnitude and the phase form. So the phase is, because omega is same for both, pi by 2. So how will the phasor look like?
So current will be on the reference line and
Yeah,
VT will
so we'll come into that, but before that, this omega into L, omega is 2 pi f into L. It's called basically the inductive reactance. Omega L is called the inductive reactance, and if you now draw the phasor, okay, and this angle pi by 2, e to the power j pi by 2 is what?
Yes, sir.
J cos pi by 2 is how much?
J.
Cos pi by 2? 0 plus j sin pi by 2. Okay, so it becomes j. So you see, angle pi by 2 can be written as j omega L Im. This angle pi by 2 is basically e to the power j pi by 2.
So I didn't understand.
Which one? This angle
Sir,
pi by 2.
the last step. The last step.
So this angle pi by 2 is e to
Sir,
the power j
omega
pi.
L Im angle pi by 2 means omega L Im cos omega t pi by plus 2.
Cos omega t plus pi by 2.
Yes, sir. Then why you
Uh,
wrote e to the power j pi by 2?
And cos is what? Real part of e to the power j pi by 2.
Yes, sir.
So that is the thing we come here. So e to the power j pi by 2 is what?
Sir, but here a real part 0.
Which one?
Real part of e to the power j pi by 2 is 0, sir.
No, this angle pi by 2 means what? Angle pi by 2 means cos omega t plus pi by 2.
Yes, sir.
Okay, so this angle is written in this form. So this Im cos omega t is Im angle 0. So this pi by 2 is e to the power j pi by 2, that is equal to j.
Sir, that is the imaginary part, sir.
Yeah. So that actually comes into this equation.
Sir, but here we are considering real part, then it is to be
So
0.
here we are basically converting from phasor notation to complex vector
Complex
notation.
value, yes.
Yes. So
you see this, if you draw the phasor, so this is, so this j, this Im angle 0, so this is basically it. Im angle 0 is it, so it is j omega L it. So what it actually means is, if you draw the phasor, where is your current? Im angle 0, that is around the
so on the
reference.
azimuthal line. Yes.
On the
And
reference.
And where is this voltage? Voltage is
Ahead
that
of
is
pi
pi by 2.
It will
pi
be
by
leading
Pi by
by
2, that is 90 degree.
Yes.
Okay. So what actually happens is this j operator. So as soon as you multiply these by j, okay, for you, j operator actually converts that, rotates the vector by 90 degree. If you forget this j
So we
omega
did
L,
this in rotation of complex number.
yes. So you have
Yes, sir.
it,
Coordinate method of rotation.
so it into omega into L are some factors, but as soon as you multiply by j, it rotates it by 90 degree. So the j operator, it advances the phasor by 90 degree. The j operator, it advances the phasor by 90 degree.
Sir, so the phasor diagram is in the complex plane.
Phasor diagram
is in the complex plane.
No, it is not in the complex plane in that sense. It is just considering the phasors, with respect to each other.
So, but when I write that it is j omega L I m, you basically mean to say that it is j omega L I m angle 0.
Yeah, so it is basically rotating it by 90 degree.
Yes, by multiplying the j factor over there.
Yes.
Yes. Okay, sir. Thank you.
So it leads to the same condition here. It is in a pure inductor L. The voltage is leading the current by 90 degree, or the current is lagging the voltage by 90 degree. Now, if you consider a pure capacitor, and if you take this Vt, you can do the similar exercise to find out the how the phasors are for a pure capacitor. It equal to Cv dV dt. And if you substitute this here, cos will give you what?
Minus sign.
Minus sign, sir.
Minus sign.
Yes, answer here.
Minus sign. I made a mistake or what? Let me see. Cos will give you sin omega t. This is minus or plus. I don't know why it is written sign in my notes. Just check it. I don't remember why it is given plus here.
Sir, there should be minus because differentiation of cos is minus sin theta.
Yeah, differentiation of cos is minus sin. Yeah, that is true. Why did I make such a mistake? Maybe it is just the magnitude, I don't know why it is given in my notes. So anyway, just this sign thing you check, I will also check, because it is even in my last year's notes also. The last year's slides. So sine is cos omega t plus pi by, or is it?
Sir, because when we write V equal to minus Q by C.
1 minute minus. Oh, I think it is okay. I think this will be minus because minus sine is cos omega t plus pi by 2.
Yes, sir. Yes, sir. Then only we will have the current
because cos
Else
omega
current will
t.
lag.
Cos omega t, no, I'm just thinking of trigonometry. Cos omega t plus pi by 2 plus omega t is in the second quadrant. So where cos is negative, so it will actually give negative. Okay, isn't it?
Yes, sir. Minus sign will be cos omega t plus pi by 2.
Isn't it?
Yes, sir. Hello,
Yeah.
sir.
Sir, screen is not appearing.
No, I know. I am correcting my slide.
Sir, can I leave, sir? I have to attend library orientation program from 5 p.m., sir.
Library orientation.
Yes, sir. I to city.
Yes, sir. Me too.
Okay, you leave today. We will start with this tomorrow. Okay.
Okay, sir. Okay. Thank you, sir.
Okay,
Thank
sir.
you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir, tomorrow will be
Thank you, sir.